Welcome to Chemistry with Caroline. In this video, we're going to look at unexpected dipole moments in conjugated hydrocarbons. So I have drawn here azulene. It's a hydrocarbon, so made up of only carbon and hydrogen atoms. And if you looked at it, you wouldn't expect that it would have a dipole moment because it's just carbons and hydrogens in there. There's not a big electronegativity difference between those two atoms, and there are no elements that would cause a dipole moment. So we wouldn't expect one, but there is one. And that has to do with the pi system here. So let's back up a minute and think about the properties of azulene. So this is a bicyclic molecule. And if I count my pi bonds, I have 1, 2, 3, 4, 5. So all around the exterior of this cyclic system, I have 5 double bonds, right? Inside those 5 double bonds are 10 total electrons. Now, when I think about characterizing a molecule as aromatic or anti-aromatic, aromatic molecules have a number of electrons equal to 4n plus 2, where n is just some number. So if I did 4 times 2 plus 2, I would get 10. So this is an aromatic ring, just like we would think of like benzene as an aromatic ring. But what's interesting about azulene is that all the exterior carbons there, have double bonds all the way around, but you have 2 separate rings in here. You have a 7-membered ring and a 5-membered ring. And neither of those rings really have an even number of electrons, right? And if we think about Huckel's rule there, 4n plus 2 for aromatic compounds, we always would need an even number of electrons to get to that. So the overall molecule is aromatic, but we have these 2 rings operating inside of that molecule. So let's go to the next slide and we'll take a closer look. So because this bicyclic system is conjugated throughout and every atom involved has an unhybridized p orbital on it that's part of the pi system, I could draw resonance structures for this molecule. And one resonance structure that I could draw would be to take these pi electrons here and move them up to form a double bond. And in doing that, I would have to move these electrons out as a lone pair of electrons on the 5-membered ring. So I'm going to draw the resonance contributor that I just drew mechanistic arrows for. So the easiest way to draw a 7-membered ring is to draw an 8-membered ring on top, or like a stop sign, and then a 6-membered ring on the bottom. Then you can just fill in your 5-membered ring on the side there. So if I look at what my arrows said, I now would have this resonance contributor. And this would be called a charge-separated resonance contributor. So the overall molecule is still neutral, but I have a positive and a negative charge within that molecule. Now, if I look at what's going on, I can even sort of treat each ring separately. So if I just look at the 7-membered ring there, I have 6 pi electrons in there, right? So I've got 1, 2, 3 double bonds, and then I have an empty p orbital that's the carbocation. And now, if I look at the 5-membered ring, this double bond here is shared, so it's in both rings, right? So 1, 2 double bonds, plus I have a lone pair of electrons. So I again have a total of 6 electrons there. And if I think again about Huckel's rule, right? 4n plus 2 electrons, 4 times 1 plus 2 is equal to 6. In this charge-separated resonance contributor, both of those rings are aromatic. Okay, so they have individual aromatic structure as each ring, and the overall molecule is aromatic because it still has 10 total electrons throughout a pi system that is full of p orbitals and conjugated throughout. So the overall character of the molecule can be represented like this, where there is a circulation of pi electrons and a positive charge around the 7-membered ring, and there's a circulation of pi electrons and a negative charge around the 5-membered ring. So the dipole moment faces towards the 5-membered ring. The 5-membered ring is partial negative overall, and the 7-membered ring is partial positive overall. So the dipole moment has a directionality as well. Now you can imagine that's not the only resonance structure you could have drawn. What if we had taken these electrons over like this and then kicked these electrons out? That would have given us this resonance contributor But now you can see that in the 7-membered ring, I have 2, 4, 6, 8 electrons. And in the 5-membered ring, I have 2, 4 electrons. And I can't make 4n plus 2 equal 4 or 8, okay? This does not work. 4n plus 2 equals 2, 6, 10. It doesn't equal 4 or 8. So this resonance contributor gives me 2 anti-aromatic compounds. So it's not going to be a significant resonance contributor because it significantly destabilizes the molecule. So you won't see it. And that's why there's a specific dipole moment with directionality for a molecule like azulene. So here's another example of an interesting hydrocarbon that's conjugated throughout. It's 2 cyclic systems connected through a double bond, but I don't really have a true aromatic or anti-aromatic structure as it is because that pi bond sort of has on average 1 electron in each ring, right? So there's like 1 electron here and 1 electron here. So I have this sort of quinoidal structure. It's not an even number of electrons. So I can look to see through charge separation if there's a way to achieve aromaticity in both rings that might explain an unexpected dipole moment for this molecule. And if you take the pi electrons in the bond that is attaching the 2 rings and localize them on the top of the 5-membered ring down there, we can take a look and see what it is we get. So that would give me a negative charge here and still the 2 pi bonds. And then I would still have my 3 pi bonds up here and have a positive charge here. And you can see now that I have a total of 6 electrons in the top ring, but it's still conjugated throughout because I have an empty p orbital for my carbocation. And I have a total of 6 electrons for my bottom ring because I have a lone pair of electrons and 2 pi bonds. So again, both of those rings are now aromatic, whereas they were kind of an in-between quinoidal type structure before. And so because of this, there's going to be a significant amount of charge separation present in this molecule, and that gives me a dipole moment. This particular direction will give me aromatic rings, and so my dipole moment faces down towards the 5-membered ring. This is the partial negative side of the molecule, and this is the partial positive side of the molecule. So this has been a look at why we sometimes see unexpected dipole moments in conjugated hydrocarbon molecules. And that is mainly due to the presence of resonance contributors that achieve aromaticity through charge separation. If you found this video helpful, please like, subscribe, and share with your friends.